Polynomial functions. So generally speaking, when you write a polynomial function in standard form, you want to write the terms so that the exponents are in decreasing order. So you start with the largest exponent and then you go in order until you get to an exponent of 0. Once it's in standard form, the degree of the function refers to that highest exponent. The leading coefficient is the coefficient of that term with the highest exponent, and the constant is going to be the term that doesn't have an x, because that exponent would be 0. So when we talk about some common polynomials that we'll be working with, if the degree is 0, we call that a constant. The equation looks like f of x equal to a number, and that's going to be a horizontal line. If it has a degree of 1, that's a linear function. And then you'll see an equation like f of x equals 3x plus 11. So the x term has an exponent of 1. And so that's going to be a line, and you're used to graphing these from Algebra 1. A degree of 2 is called a quadratic. We spent a lot of time this year working on this. And you'll have an equation with the highest exponent of 2. So you'll have an x squared term. Your graph will be a parabola that either opens upwards or opens downwards. If you have a degree of 3, it's called a cubic function, and your highest exponent is going to be a 3. So you'll have an x cubed term, and that's going to look like a sideways S. So it can go from down to up or up to down. A degree of 4 is called a quartic function, and again, you're going to have an exponent of 4, so you have an x to the 4th term, and this graph is either going to look like a W or kind of like an M. Here we need to decide whether the polynomial function, write it in standard form, state its degree and leading coefficient. So here we want to take our terms. We have an x squared, an x to the 4th, and a constant. So we want to write it in standard form. So the highest exponent is x to the 4th, so we write that term first, negative 3x to the 4th, and then we write the term with the x squared plus 1/2 x squared, and then lastly the constant, negative 7. So yes, this is a polynomial function. The degree, that highest exponent, is 4, and the leading coefficient is negative 3. When we look at example number 2, we have exponents of 3 and x. And the problem here is you cannot have a variable for an exponent in a polynomial function. So this is not a polynomial function, and you cannot fill in the rest of the information. In example 3, we run into another problem where we have an exponent that is a negative number. You cannot have negative exponents, and so again, this is not a polynomial function, and we cannot fill in the remaining information. When you take a look at example 4, we have x to the 1st, x squared, and this is a constant because it doesn't have an x term with it. So don't get thrown off by decimal coefficients, pi, or radicals. Remember, those are just numbers stated in a different form. So let's go ahead and put this in standard form. We have f of x is equal to, our highest exponent is x squared, so we have a positive pi x squared, and then we have this term, negative 0.05x, and then lastly we have our constant, minus square root of 2. So yes, this is a polynomial function. The degree, highest exponent, is 2, and the leading coefficient is pi. So next let's talk about end behavior. And when we're talking about end behavior, we want to know what is happening at the ends of the graphs as we approach positive infinity on the x-axis and positive infinity on the right. So as our graph approaches positive infinity on the x-axis, that's in the right direction of the graph. And as x approaches negative infinity on the x-axis, we're talking about what's happening to the graph as we follow to the left side. And our answer is either going to be the graph is going to go upwards into positive infinity, or the graph is going to go downwards into negative infinity. So let's go ahead and take a look at the 4 common polynomial functions that we're going to be discussing. When you have f of x equals x, this one, as we go to the right, it goes upwards. So as you go to positive infinity, our function is going towards positive infinity. As you go towards the left, or negative infinity, our graph f of x is also going downwards towards negative infinity. In f of x equals x squared, as we go to the right, our graph is going up towards positive infinity. And as you go to the left, our graph is also going up towards positive infinity. F of x equal to x cubed, as we go towards positive infinity to the right, our graph is going up towards positive infinity. As our graph goes towards negative infinity to the left, our graph is going downwards towards negative infinity. And in f of x equals x to the 4th, as we go towards positive infinity to the right, our graph is going upwards to positive infinity. And as we approach negative infinity to the left, our graph is going upwards towards positive infinity. So I want you to go ahead and try the 4 on the bottom and then check back with me when you're finished. So you should notice that the change in the bottom set of graphs is they're the same as the top set, except they're reflected over the x-axis. So when it gets reflected or flipped upside down, all of our end behavior is also going to switch. So our linear function, as you approach positive infinity, this is going downwards to negative infinity. And as you approach negative infinity, our graph is going upwards towards positive infinity. Our parabola, both of our end behavior is going down towards negative infinity. And then our cubic, towards positive infinity, it goes down to negative infinity. Towards negative infinity, it goes up to positive infinity. And then our quartic function, the end behaviors, they're both going downwards to negative infinity. If we want to summarize the end behavior of these 4 common polynomial functions, we can categorize them by degrees and by the leading coefficient. If you look at even degree polynomial functions, their end behavior will be the same. So if the leading coefficient is positive, they will both go up to positive infinity on the end behavior. And if the leading coefficient is negative, both of the end behaviors will go downwards. If the function is odd, then you're going to have different end behaviors. One will always go towards positive infinity and one will go towards negative infinity. So if it has a positive leading coefficient, then as it goes towards positive infinity, it will go up, and as it goes towards negative infinity, it will go down. And then if it has a negative leading coefficient, as it goes towards positive infinity, it goes down, and as it goes towards negative infinity, it goes up. So it flip-flops. There are a few important features of graphs of polynomial functions we need to discuss. They have only n minus 1 terms, where n is the degree of the function. So in this first example, this has a degree of 3. So 3 minus 1 is 2. So this function has at most 2 terms if we were to graph it. Example 2, we have a degree of 5. So 5 minus 1 is 4, which tells us that at most this graph will have 4 turns. A function of degree n has at most n number of x-intercepts, and the x-intercepts are the zeros of the function. So at an x-intercept, the value of the function is 0. Remember, we've talked about this before. In order to find an x-intercept, you want to solve for x when y equals 0. The y-intercept is when x equals 0. So your y-intercept will always be found as the coordinate point 0, comma, and the constant value. If there is no constant in the function, then it's 0. Next, we want to talk about maximums and minimums. And remember, maximums are the highest points, minimums are the lowest points. But even within a max and min, we want to talk about what it means to be absolute versus local. In this parabola, This is an absolute maximum because there is no point that on the graph that is higher than this one. However, if you look at this graph, you have this point here, which is kind of at the top of the hill, but you have other points on the graph that are higher than that point. So we call this a local maximum. The same idea for minimums. Here we have this point on the graph which is lower than any other point on the graph. So this is an absolute minimum. And then here we have this part of the graph that kind of dips down and goes back up. That is a low point of the graph, but it's not the absolute lowest point. So we call that a local minimum. Now here we want to work out this example where you're given a polynomial function and you want to draw a sketch of the graph and answer the following. So let's go ahead and answer the information in our chart that we can just from looking at our function. The degree is the highest exponent, which is going to be 3. The maximum number of turns is always the degree minus 1, which gives us 2. And the leading coefficient here is -1. Next, we can also answer the y-intercept because it's always going to have an x-coordinate of 0, and then your y-coordinate is going to be the constant. Now, we mentioned this before, but because this doesn't have a constant term, it's going to be 0. And then we can also talk about the end behavior. Because this is an odd function, we know our end behaviors are going to be different, and because it's negative, it's going to go from up to down, and this is a general sketch of our cubic. So we know that as x approaches positive infinity, f of x will go towards negative infinity, and as x approaches negative infinity, our f of x will go towards positive infinity. To find the x-intercepts, you need to put your function into the calculator, take a look at the graph, and you want to calculate the zeros of the function. When you do that, you'll get -2, 0, 0, 0, and also +2, 0. For the minimum, you want to calculate the minimum on the calculator from the graph, and you'll get -1.15, comma, -3.08. And same for the max. You're going to calculate the max from your graph, and you get +1.15, +3.08. And then we can go ahead and plot our points and sketch our graph. So we're going to plot the points that we have, -2, 0, 0, 0, and 2, 0. We don't need to plot the y-intercept again because that was also one of our x-intercepts. Our min, we're going to approximate -1.15, -3.08, and then our max, +1.15, +3.08. And then we know that this is going to be the general shape of our graph, so we're just going to try to connect our points in a general fluid motion. So this is going to be the shape of our graph. Then for the domain, it'll always go towards the left and right, so it goes from negative infinity to positive infinity. In our range, it'll always go down and up, so it goes from negative infinity to positive infinity. And that's it for this video.